Thank you for joining me on this question. We're going to be looking at another question about permutations. Now, permutations we've done previously is where you can select each letter, and here we've got a word. We're going to use the word mathematics. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has 11 letters. Now, we're going to be looking at permutations, and permutations is where order does matter. So if you move things around, you've got a different permutation. What we've got above is one permutation. And the question is, how many permutations can we make using these 11 letters? And we want to use the entire group of 11 letters. So we've got 11 positions. And previously you would have learned that we could choose any one of the 11 letters for the first position, which leaves 10 remaining for the second position, 9 for the third, 8 possibilities for the fourth, and it continues all the way until you've got down to only one choice for the last remaining letter. Now, we've learned that this is 11 factorial. That's a very big number. I will just say, well, let's just not worry about how big the numerical value is, but 11 factorial is the value that we're talking about. This is in terms of factorial. 11 factorial, by the way, is when you start at 11 and you multiply each number all the way down to 1. And so that is why we call it 11 factorial, because there's all these factors in that particular calculation. The thing is, are there really 11 factorial different permutations? Now, if I just find out what is 11 factorial, let's just quickly find out approximately what is 11 factorial as a value, and the calculator says, if it's not correct, we've got 39 million, almost 40 million, 916,800. That's the numerical. I wasn't going to do that, but I figured, well, why not? Okay. So we're talking about almost 40 million ways that you could rearrange those 11 letters. But are there 40 million? Are there different permutations? The concept is order does matter. So different representations. Now, if I just make this M a red, and if I make this M a blue, wouldn't we get the same word if we swapped that around and we had the word we'd still see the word mathematics, right? But the thing is, in one permutation, we've got the blue M first, and in the other permutation, we have the red M first, and you swap them over, and you can actually end up with two words which look identical. They both say mathematics. So they're not, in fact, different permutations. It's because there's two M's. And out of those 40 million, two of those words have a doubled up. So we've got, and in fact, that's if we put M in those positions. And if we move it around, no matter where the M's go, we could double up. So really, it's not 40 million at all. It's only 20 million, because let's say we have a different permutation, and let's say we've got a MM, and we've got all the other 2, 4, 6, 8, 10. Now, we could have that M there and that M there, and we would end up with 2 words which look identical. So really what we're saying is every different permutation you get, they're doubling up. So it's not really 40 million, it's about 20 million. Now the thing is, let's look at the A and this A. Let's make that a yellow A. Wow. Does that mean that if we swap the A's around, we would get M? Let's put that black A there, and let's make that a yellow. We could have a yellow A there, and still the blue and the red M's are the same, but we end up swapping the A's around. And you see, because there's 2 A's, now we're going to actually have the word mathematics appear 4 times, and it's because if you swap the A's in different positions, you can end up with seeing the same word, but they've just moved the A's around and the M's around. Now what we're saying is it's not in fact 40 million, because now every word's going to appear 4 times. And so it's really 10 million. And so this word also appears another. So every different permutation appears 4 times. Well, are we finished? No, we're not, because you will see that there is in fact a T here and a T here. Now, we could swap those around, and if I take these 4 words, and here I put the blue T's here, let's put the blue T's there, and put the red T's here. Yeah, there's 4, but I can get another 4 simply by changing those blue and red T's around. And so we would end up with, in fact, 8. And I will just do one of them. I'll put, we have so this first word here, M, a black A, and instead of the blue T, I put the red T in that position. And we've still got only one H, one E. I'm just going to put that red M in that. I'm leaving this first word almost identical. All I'm doing is swapping the T's around, the blue and red T's. And you see this word here becomes that word if we swap the T's around. And therefore we've got all together, each word appears 8 times. So here's how you do it, okay? If you've got M appears twice, A appears twice, T appears twice, and all the others appear only once. So if we've got 11 factorial, we've got to divide by, because this one appears twice, 2 factorial. This one appears twice, 2 factorial. The T appears twice, divide by another factorial. All the others appear once, so we're finished. And you end up with 11 factorial divided by 2 factorial times 2 factorial times 2 factorial. So that becomes divided by 8, and you would end up with the answer let me just take that original number, 3,000. I'm just going to divide this offline because it's easier. So I'm going to take 39,916,000. Let's do that again. 39,916,800. Divide that by 8, and we get 4,199,600. And there's our total number of permutations that we can make using those 11 letters. Only almost 5 million different permutations, because they appear, each one appears 8 times, so they're not different at all. And in saying that, look, if one of those letters had appeared 3 times, then you would have divided by 3 factorial for that particular situation. So I hope that's helped. And this is when you have double ups. So be careful and apply this concept, and you should not get it incorrect. Until next time, stay happy.